Welcome to the Quantum Feedback Loop podcast. I'm your host, James Myers, and I also publish the Quantum Record. I was pleased to meet with Alec Koumjian, Head of Software Engineering of the Asteroid Institute. In this episode, Alec speaks about the B612 Foundation's mission to detect and map asteroids and other space objects that could pose a threat to Earth. Alec provides some fascinating details of the efforts underway for planetary defense, outlining the development of the Institute's Atom software platform that uses observational data to predict the paths of objects over very long periods of time. It was fascinating to learn how much is being done to protect the Earth and how much more can be done. And I hope you learn as much from this discussion as I did. Well, hello, Alec. Welcome to the Quantum Feedback Loop podcast. And I'm really interested to learn about your work for the B612 Foundation and the Asteroid Institute.
Thank you, James. Really happy to be here, and I love talking about what we're doing.
Well, that's great. So maybe to begin with, if you could tell us a little bit about the mission of the B612 Foundation and its Asteroid Institute, and then also what your role is. I understand you're leading a team of scientists and engineers for it.
Yeah, absolutely. So the B612 Foundation is a nonprofit organized around the purpose of planetary defense specifically. So namely, preventing asteroids and other objects from impacting the Earth. And the idea behind the program Asteroid Institute is to get together software engineers and researchers to develop the tools in order to accomplish that goal.
And I understand that the Institute's program, the Asteroid Discovery and Analysis Mapping Program called ATOM, that's, I guess, an innovation of the Institute, is it? It's not has anybody else tried to do anything like this?
So ATOM is the name of our kind of hosted compute platform. You know, it encompasses a variety of data sets and software services, and it's essentially the the umbrella under which we are trying to build out all the foundational pieces that we will need in order to achieve kind of the ultimate goal, which is this idea of this generating a map of the solar system, which is kind of what you need to do in order to know if there are objects heading your way.
And so with this map, I guess to the extent that we have a really accurate map, we would know of potential threats to the Earth. Then I guess that leads to a question of how we defend the Earth from those threats.
Yeah, so those are kind of the two sides of the coin, so to speak.
Right.
And B612, has broadly worked on topics on both those sides. And the Asteroid Institute, at the moment at least, is mostly focused on basically that discovery and tracking side of things. We already kind of collectively as a species largely know about many of the objects in the solar system, in particular, a lot of the very big ones. But there are still gaps in our knowledge there. And so we kind of have to take this holistic approach where, we're not just taking those known objects and trying to get a better understanding of where they're going to be, which is its own whole kind of problem. But then kind of more foundationally, out of the data sets, astronomical data sets that are out there, how do we extract the most knowledge out of those and discover the most objects so that we can then into the future try to predict where they're going to be?
Interesting. And I want to talk a little bit about the science of that and what's involved in that. But I wonder first, just maybe if you could sort of position it for us in terms of how many objects are out there that we know about and how many are hitting the Earth regularly. And I ask this question because, I'm based in Toronto, and actually not too long ago, there was a rock from outer space that came and struck not too far from the city here. And so that kind of hit home literally, I guess. And so I'm wondering, I think a lot of these are small objects, right?
Yeah. And so while I'm probably not the foremost expert on the ongoing statistics, but to kind of like paint a picture broadly, basically there are a variety of different populations of objects of different, mass and energy that they have. And everything from believe it or not, we are constantly being bombarded with micrometeors all the time, right? Like tiny molecular size objects coming through our atmosphere and being studied and collected, all the way through things like the Chelyabinsk event, which was when a very large meteor exploded in the sky and shattered all of the windows, all of the glass in that area, to the kind of cataclysmic, popularly known dinosaur ending size objects, which my understanding is that, roughly over the history of the Earth, objects like that may have hit, every 50 to 150 million years or so. And so, we know about, we believe theoretically, basically are tracking all of the world ending size objects out there, and unless there was something very unusual to come, say, from out of the solar system. But then it's kind of, you get down in size, we know a smaller and smaller percentage of, say, things that have the energy that could cause serious damage for cities, or, and then smaller and smaller sizes. So, objects of various sizes do hit every now and then. I don't think we have to worry about anything world ending, but there are still objects out there that could have significant negative impact and world implication. And so we want to kind of complete from the, 60% of those objects we believe track to close to 100%.
Mm-hmm. Interesting. And actually, you mentioned Chelyabinsk, which I guess was in 2011, I think, in Russia.
That sounds correct.
Yeah.
Yep.
Yeah. And that one, I guess, kind of came out of nowhere. There was no warning for it. And I guess to the extent that your project is to map the trajectory of these objects in space, we would have more warning of things like that. And I guess it was fortunate, I guess, that there was no loss of life, I don't think, in the Chelyabinsk incident, but it could easily happen. So it's an important project for sure. And interesting, actually, now that experiment, when was it, last year or the year before, with the asteroid deflection, that actually, the probe that they sent out to deflect it. So we actually, with this knowledge, I guess we can actually do something about it maybe now.
Yeah. And so this is not an area that I am extremely knowledgeable about, but yeah. So with the DART mission, part of it was just to see, when you have an impactor going into one of these objects, like what happens, because there's still a lot of unknowns about, say, the physical construction of many of the objects in our solar system. And so, even knowing, like, is it kind of like a loose pile of rocks and sand model, or is it more like a solid object model? And so what happens when you have this impact? Predicting what's going to happen is extremely difficult. And, for practically speaking, for preventing an impact long term, you need to be able to say with confidence where it's going to be years in the future. And you're trying to, your ability to change its velocity is very limited. And so what you aim for is a small change in velocity years in the future, in order to, just wholly avoid where the Earth was going to be at a particular moment in time. Yeah. So it's almost more about time than speed and location.
Yeah, that's really interesting to think about, that time dimension of it all. And I guess how far away some of these could be, but how just a very small change in direction over time could make all the difference. So yeah, really interesting. And so I wanted to maybe just start talking a little bit about the science and the complexities of this. And so I understand your education was both in computer science and physics. And I'm just wondering, what are some of the innovative way those two branches of science in particular are being brought to bear now, on this research and work?
Yeah. And I think part of that, bringing those two areas together, is kind of largely the idea behind Asteroid Institute, which is that there are, with the scale of types of science that we are trying to do, you can't leave the algorithms that you are running, say, on your data sources, to just whatever works. You actually have to consider kind of core foundational computer science topics, like how efficient is the algorithm, right? We talk about like big O notation and complexity. And if you're running this software in a way where it has to, the number of calculations that it has to perform, they can balloon very quickly. And so the computer science end of things is looking at those with kind of some very foundational ideas behind computer science, and how you can do things more efficiently. Are there data structures that will kind of fundamentally change how you do the science? And then, of course, on the physics side, there's all sorts of tools that we use, whether it's like propagating where an object is going to be in time, or doing fitting an orbit based off of observations, uh, there are many shortcuts, right? There's numerical shortcuts and analytical shortcuts, and a lot of the time you can write software that looks good, but what it's producing is maybe like non-physical or non-real on the other side. And so in everything we do, you're looking at it from the perspective of generating results that are real physical models.
I can imagine so many calculations would be involved with all of these sort of interacting bodies in space, and gravitational interactions and all of this. And so the team of the group that you're leading, I guess, would involve people from a number of different disciplines, like maybe astronomy. And can you give us a sense of sort of the range of knowledge that's being brought to bear on this question?
Yeah, absolutely. So we have a wonderful but small team at Asteroid Institute. So there are essentially, not to bucket people too much, but we have 3 software engineers, not including myself, and then we have a research scientist. So those software engineers are Kathleen Kiker, Nate Tellis, and Spencer Nelson. And then we have Joachim Moyens, he's our researcher at the University of Washington. And then there's myself, and then we also have a handful of volunteers who very dedicated volunteers who help us with a variety of projects as well. And so that expertise it ranges from people who have worked at telescopes or for defense companies, or just hot, in the case of say myself, just like hobbyists in terms of as far as the astronomy goes. And then you have like Joachim Moyens, who's our researcher, who's coming from the Dirac Institute at University of Washington, where they do kind of the very heavy astronomy and computation. But we are a team where we are, all trying to wear various hats, I guess, trying to be interdisciplinary in that approach. We're not heavily segmented into our areas of expertise. It's very collaborative.
And what are some of the practical hurdles that you're working on to overcome in reaching the goals of the Atom project, and more generally planetary defense? Like, what are some of the biggest hurdles in that whole project?
Sure. Well, some of them, unsurprisingly, have to do with data. So first, we need to discover the objects, and that involves collecting as much data as we can. So right now, Atom has a catalog of moving point sources. These are detections of light in the sky that are likely to be from moving objects. So this is already data sets that have filtered out all the static sources, all the stars, basically. And that comes from a variety of different sources, right? It comes from telescopic archives like NOIRLab Source Catalog. It comes from active surveys like the Zwicky Transient Facility. And so some of the challenges that we have are just like practical software engineering issues, right? Like in getting in all these data sets, not all these systems are set up for kind of bulk retrieval of that data. We work closely with those other organizations to absorb them. There's making sure they're accurate, right? We've had to identify issues like observations being marked, say, at the beginnings of exposures instead of like the more technically correct middle of an exposure time, and that makes a big difference when you're trying to precisely locate the position and time of an object. So there's challenges like that, kind of like data engineering challenges. There are algorithmic ones. So we have a discovery algorithm called Thor, which I'd love to talk about more.
Sure.
And one of the things we are doing is adapting it better to orbits of near Earth objects, since obviously that's of concern to us. And part of the problem is that the way those objects move and the shape of their orbits are they're nonlinear. They're more curved when we look at them, and this causes the way that Thor works to essentially it requires a lot more computational resources in order to kind of try to pull those out and discover them. And so there's challenges like that, and then of course getting other practical organizational challenges, making sure we have the funding that we need to run the computational jobs that we have, and we have a variety of great supporters, and we work with organizations like Google to help provide us some of those resources.
That's great to hear. And so, yeah, maybe tell us a little bit more about Thor. So this is part of the Atom project. What does Thor stand for?
Yeah, so Thor is bit of a mouthful: tracketless heliocentric orbit recovery. And Thor gives in a category of algorithms that we call linking algorithms. And the idea behind this is that when you have telescopes pointed to the sky and you are taking pictures of points of light, you essentially have this giant game of connect the dots where you're trying to figure out what points of light between different images belong to the same object. And so kind of traditionally the way this is done is that a telescope will take two images close together in time of the same point in space, and you will get small movements of points of light, which are relatively easy to find between those two images, right? Because you have only a handful of dots moving, and they're moving very relatively short distances. And from those you call those tracklets. And then you group those tracklets together, maybe over multiple nights or something. And that will, on the other end, you've discovered an object. So what Thor does, which is a little bit unique, is that it doesn't depend on the cadence of the telescope. So you don't need to take those two images so close to each other. Instead, you can take virtually an arbitrary data set, such as, for example, the deep energy camera DECAM, which is not meant for solar system science. They're not doing a cadence where they're, tracking asteroids intentionally. So what Thor does differently, essentially, is you start with an assumption, which is test orbits. You'd say, suppose there was an object that looks like this, and it was moving through space like this. You project those test orbits through your observations where they are in time, and you're making assumptions about those observations too, like distance from the sun, as an example. And when you project that test orbit through those observations, and then you map where those observations would be relative to the perspective of that test orbit, objects that are moving like that test orbit, they show up kind of as lines or clumps in that reference frame. And so when we call those clusters. And so then what you can do is you just look for those clusters in the reference frame of the test orbit. And then you basically can move on to perform traditional orbit fitting on those observations. And then when you have basically good matches, things that look physical and realistic, you now have theoretically an object discovery coming out the other side.
Well, that's fascinating. And so I guess as you said, it allows you to use more data sets, I guess, that aren't necessarily intended to be correlated to each other. So it's a way of establishing a correlation where there wasn't one before.
Yes, that's right. And so the time between the observations is not as important. It can be a highly irregular, cadence of those observations. And again, you can get them from data sets which were generated not meant to look for asteroids or other solar system bodies intentionally. And one of the things that we're hoping long-term with that is that you can actually free up, surveys to do other types of science, spending less time kind of going back, generating those tracklets, but still discover the same amount of objects on the other side. And that can be, very important for, the amount of science that a telescope can do.
That's great. And it really sounds innovative in terms of new ways of approaching such a large amount of data. When you said connecting the dots, I had this image in my head of just so many dots out there to connect. And so, yeah, it's great that we're able now to really be, I guess, to really advance along that science in a way that hasn't been done before. So I'm just wondering, is there a particular milestone that you're working on now with Atom?
Yes, absolutely. And it relates to Thor, and I'm personally very excited about it. So in the past couple of years, Joachim Moyens and the University of Washington and Asteroid Institute, they came out with the paper on Thor. And then shortly after that, we ran Thor on a small subsample, a 30-day window of that Noir Lab source catalog data set, and discovered 104 asteroids out of it. And so since that time, we've been basically getting ready to gear that up. And so this past year, we've been working on some other foundational pieces, namely a service called Recovery, which I can talk about too, which we use as kind of a sub component of Thor. But now what we are doing is getting ready to run Thor on the remaining 99.8% of that Noir Lab source catalog. So that has involved making it more efficient and robust to errors, and developing the tools that we need to kind of scale up on lots of machines in the cloud and perform a lot of computations.
Well, and how long do you think that 98% or 99% of the catalog would take?
Well, that all depends on how many simultaneous cores that we have running the job. The great news is that it's highly parallel, right? So every test orbit that you're sending through the sky can be run as its own process on its own machine, basically. And so I think when we are running at full steam, so to speak, I'm hoping, sometime between 2 to 4 weeks to crank through that whole data set, but it could be longer depending on how many resources we have available in the cloud, like literal machines on those systems that we have available to run, and also how expensive those machines are, unfortunately factors into it as well.
Yeah, that's always the case, I guess. And I guess to get a sense of the amount of data that you're looking at, obviously you've indicated it's a large amount of data from many different sources. Are you looking primarily just in the solar system, or are you also looking outside the solar system?
Well, so there's kind of a few ways of looking at that. So our ability to look for certain objects, I mean, it's within the solar system, and what we can find is first limited by the limiting magnitude of the source data sets, right? Like the source telescopes, which in some cases is quite good, again, because we're looking through even non-traditional solar system data sets like from DECAM. But in terms of what we find is also largely going to depend on those test orbits that we run through the system. And so I don't believe we will be sending through too many test orbits. That would be, it's really just the range is the scope of the space of test orbits that is likely to exist within our solar system. But there's always kind of interesting room to say run through some highly unique and unusual orbits and kind of see what comes out the other side.
Mm-hmm. And are you partnering with any other institutions? Like you mentioned the University of Washington, I think. Are there other institutions that are involved in this project?
Yeah, so I mean, we have University of Washington. We have the specific research program through. We are not for this specific. Well, so for the Noir Lab source catalog, obviously we are working with them to the extent that they've been very good at helping us collect that data for us to use it in our systems. Similarly, all the other organizations that we get our data from, whether it's ZTF, we've been working with Atlas program out of University of Hawaii, which is a bunch of different telescopes, SkyMapper, folks at Catalina. So these are all different organizations, mostly telescopes, that surveys that we've worked with, and people that have graciously helped us with, even providing like custom exports of their data in order for us to ingest it. Google has been a great partner. They've helped us not just in terms of making compute resources available to us, but providing a lot of technical guidance. And we've held events where we meet up with folks at Google and talk about the various problems and kind of variety of different services and ways that we can expand our initial goals with what they have available. And then we also work with organizations like the Minor Planet Center, which is, for those not familiar, is like the clearinghouse of objects in the solar system. So when someone discovers a potential new object, they will submit it to the MPC, and they will essentially verify and do a bunch of other things to maintain that list of known objects. And so we've worked with them to, as both a submitter and when we found odd discrepancies in data sets that have working to correct problems like that, and they've been a great group to work with.
And so you mentioned pre-covery, so maybe if you could just talk about that. And then I wanted to ask maybe a little bit about machine learning. So maybe just start with pre-covery.
Yeah. Uh, so the idea behind recovery is that typically you have an object you're already thinking about, or many objects, and you would like to know if there are additional observations out there for this object. And the reason you would want to find additional observations is that when you have more observations of an object, you can now basically generate a more precise orbit, for a more accurate orbit, I should say, which can make a huge difference in terms of where it is, and especially for concerns such as planetary defense. And so, there are many institutions that kind of they've have their own versions of recovery, and there are other public recovery services available where you can take an orbit and basically get back a bunch of candidate images that may or may not contain a point source of the object in question. Adam's version of recovery is a little bit is unique in the sense that so first thing is that, and this is available for people to use, they can go on our website and either look up a known object or put in a theoretical orbit of something, and they can scan the roughly 5.3 billion point source observations that we have for that. And then what we do is we're able to actually, in just minutes, produce back not just the potential images, the potential exposures, but actual point sources that may belong to that object. So typically what you would do is, after getting your list of candidate images, you would then have to kind of scan through that and say, oh, where would my object be in this image? And is there a point source there? And what we're doing is we're essentially doing that for you. And we're saying, this is where it was predicted to be. Here's even the predicted velocity. So you can say like, oh, does the trail match up with what I'm looking for? And so that's recovery. And it doesn't have to be before the discovery, which recovery implies. It can actually be more recently. So there's an example recently. Other folks at University of Washington and Vera Rubin Telescope, they used a different linking algorithm called HelioLink against the Atlas data set, and they discovered a potentially hazardous asteroid with it. And then we were able to then take that new object and run it through our recovery service, and we found a bunch of new observations from ZTF in just a couple minutes. So that's kind of an example of what you might use recovery for.
That's really interesting. And so can the public go on and submit observations as well as other scientists?
Yeah, so anyone can go on our website. We have basically a website demo version of recovery where you can go in. We make it convenient to say search the small bodies node for, say, like a named object, or you can just put in the orbital elements by hand if you want, if there's something different that you want to look for, and run it through that recovery service. And then you'll get a page that has nice cutouts of all the different observations it found. And then we don't quite have it ready, but we're working on building a whole pipeline to try to make it easier for people to prepare submissions to that Minor Planet Center off of new discoveries. So that would be kind of a tool or an interface where people can take not just recovery, but other things and do the necessary work to kind of validate and prepare the submissions so that MPC can look at it.
Interesting. And so you mentioned, I think earlier, it was 104 asteroids were discovered. Is that the contribution so far, or has there been more discoveries?
So let me think. So from Thor specifically, that's the main submitted contribution so far. Thor was also run against the ZTF data set in order to basically do a completeness comparison, because ZTF does discover asteroids, and so Thor was kind of run against that to see head to head how many could it recover out of that. We've also done a number of submissions, not of new discoveries, but recoveries of what are known as the JPL and ESA riskless. So these are the objects that have some non-zero chance of hitting Earth someday in the future, and so we regularly take those. I think it's like roughly 1,200 objects or whatever it is. run them through Recovery, and generate new, when we find new observations of those, we submit those in kind. So we are gearing up to do hopefully many more discoveries with Thor, and part of that is kind of building a whole pipeline around processing all the results and making sure all our T's are crossed and I's are dotted before submitting.
Right. And the JPL is the Jet Propulsion Laboratory, NASA's JPL. I guess, and I've actually been on that site to look at their list of near Earth objects, I guess. So eventually, is that list then you would be adding to or adjusting that list, I guess, over time?
Yeah. So by refining the orbits, what happens is once new observations would get accepted into the Minor Planet Center, then JPL will essentially at some point take those new observations, and they have their own system where they will kind of recalculate the orbit with their system, and then they do basic an analysis that provides impact probability chances off of that.
Yeah, interesting. And so now, I wanted to ask about machine learning because I gather that's maybe something that is not being done yet. But to the extent that funding permitted, is that something that you would be pursuing? And is there other, kind of major avenues that you could explore with more funding for your project?
Yeah, absolutely. There's a variety of different cases. Some of the most straightforward ones are take Recovery, for instance. All the time, it's easy for us to come up with candidates for new observations for objects, but it often takes additional analysis, and many times that's still not automated. We have to have a human look at the candidate and say, is this realistic, or is it an artifact in the image, or is it obviously trailed in the wrong way, or is this not a moving object? There's just bad seeing between two different nights, and the catalog, or we thought it was a moving object, but really it's a star or something. And so I think it would be a slam dunk to use what are now considered pretty traditional machine learning algorithms to say categorize those candidates as basically probabilities of being good or bad. Some other potential areas would involve say deciding which test orbits for Thor to run through a particular data set. Test orbit selection is something we talk about a lot because it has a big impact in terms of how much computation is performed and what comes out the other side. And so, a potential version of Thor that would, use machine learning, taking the some knowledge about the input observations and being able to automatically recommend certain test orbits within that selection, I think would make a big difference in terms of cutting down on unnecessary computation and kind of maximizing the discovery that comes out the other side.
Yeah, imagine. And so this would be both unsupervised and supervised machine learning. I guess both could be used.
Yes. Yeah. Yeah, probably in both cases, you could probably use both supervised and unsupervised.
Oh. Is there any other technology coming online or proposed that would help in the whole mission of planetary defense? I think you mentioned the Vera Rubin Observatory, which has it started yet, or is it about to start?
So I think I believe the current schedule is, I think they're getting it's going to be at least over a year before Vera Rubin is coming online, and that is going to be kind of a shift in the whole landscape in terms of how the science is done. Just from the sheer volume and size of the data that it's going to produce is going to be orders of magnitude greater than what we have so far. And so when we think about this a lot, because when we talk about kind of Atom and making the platform scalable, one of our biggest goals is being ready to adapt to the scale of Vera Rubin and the LSST survey, because it's going to basically require 10 to 100 times more compute easily than what we could do now based off of existing surveys.
Well, that would be a major leap. Yeah, it's interesting to think about all of not just planning for current technology, but also for future technology. So it's good to know, I guess, that there's that new source that's coming on soon, and yeah, hopefully the resources are there to be able to process it all. I wanted to ask, I understand there was a Pew Research Center survey conducted not too long ago that indicated actually surprisingly high number of Americans are concerned about planetary defense, because I guess it doesn't get a lot of press. But in terms of space exploration, I understand that 60% of Americans think that the first priority for space exploration should be to monitor asteroids and other objects that could hit the Earth. And I'm wondering, how that high level of public interest is affecting your work. And then also, is there anything that the public can do to contribute to your work?
Yeah, thank you. So we saw that study as well, and we thought it was particularly encouraging given our interests. I would say that that study and the broad interest hasn't, to my knowledge, broadly impacted the work yet that we're doing. We don't currently have any citizen science opportunities live right now. It's definitely something we would like to get involved with, aside from the fact that, if there are people out there who are maybe more software inclined, we do welcome volunteers to kind of join us and work on we have a variety of open source libraries that we develop, and we very much welcome help and contribution for those. And then we hope that just, broadly the public support for our mission encourages other people and groups and organizations to get involved in terms of funding ours and other programs to try to make this a more or less solved problem, because it is tractable, and we think that if with enough support that we can build essentially that map of the solar system and keep it continuously updated and have a lot more knowledge about what's out there, and prevent any potentially hazardous impacts.
And B612 does accept donations from the public, so I guess we can encourage any members of the public who are interested to contribute financially as well as with their time if they have.
We would love both.
Yeah. Well, that's great. Listen, we would love to follow up on the work that you're doing and just to see how it develops over time. It'd be really interesting to share the story with the public, and hopefully some good news. I think it sounds like you're really tying together so much in a very innovative and pioneering way that something definitely good will come from it. And so we'd like to be there and really understand what it is and let people know. I think it's good, with so many people interested in planetary defense. It'd be good to show them that there are good groups of people like your group who are working on the problem very diligently. So that's great news, and we really appreciate your time sharing the story.
Well, thank you so much, and yeah, we hope to continue to be hard at work so that we have some really interesting and exciting things to share with folks.
Indeed, and we all hope that your mission of defense produces great results, because we all depend on it. So. Well, thank you very much, Alec. It's been great speaking to you, and we'll look forward to following up with you in due course.
All right. Thank you very much, James. Glad
Thanks.
to be here.
Our thanks go to today's guest and to you for listening to the Quantum Feedback Loop. Please subscribe to this podcast wherever you get your podcasts, and don't forget to check out the Quantum Record at thequantumrecord.com. The Quantum Record is a monthly journal of philosophy, science, technology, and time, where you'll find the latest developments in our rapidly evolving technological world.